Okay, so I'm going to be talking about this title, but the title is different. So it's the deep learning theory beyond the kernel limit, but the content is going to be similar. So the grand theme here is, I guess, what we're looking for is basically, deep learning is complex. It depends on many parameters, hyperparameters. It displays like complex dynamics and so on and so forth. So is there a sort of a reduced, simplified description of deep learning dynamics? That's going to help us interpret it, understand it, perhaps better use it for engineering purposes and science. So that's the grander spirit of it. And, as physicists, we are sort of used to these kinds of simplified descriptions and reduced descriptions, and that's something we often strive in our work, and we're familiar and we value this kind of work, which is nice to be among such people. Okay, and in particular, in arrive at such limits or such descriptions, one of the things we might be doing is looking at limits of systems. And in particular, in deep learning study, there was this particular limit that has been very influential and helpful in getting some insight. And that is what I'll call the large network size limit. In particular, I'm going to be talking about the deep feed-forward networks today. And by large network size limit, I will be meaning actually large width limit. And by that, I also mean the following thing. So just as a graphics, I'll demonstrate my neural network like this. There'll be some layers of, neurons acting on, or units acting on their pre-activations, which derive from previous layers and so on and so forth. And X will be the input, and f of X will be the output. I'm drawing here 3 layers, depending on how you count your layers. But today, what I'll say actually will apply to many layers, not just 3 layers over here. Okay, so given this, what do I mean by a, sorry, just trying to figure out this one, okay. Infinite or large width limit is the following idea. If you keep adding more and more units to a particular sort of layer, and I'll call the number of units in that layer n, okay. And as this n is going to infinity, depending, and we're going to talk about of course, scaling in a second, depending how you scale your parameters and so on and so forth, you might end up getting with basically some simplified descriptions of the complexity of these neural networks and their dynamics. In particular, there's a particular way this has been taken to infinity, and this is called the neural tangent kernel limit. Okay, and I will describe more about this in a second. That has given a very sort of nice description of what happens. So the particular way this works is what you do is you initialize your neural network by choosing your weights, okay, from a basically normal distribution, but scale it in a particular way with 1/√10 right over here. I'll use my pointer here, okay. And the reason you might want to do this is because sorry, this is not showing. The reason you might want to do this is because because of central limit theorem, basically. As you keep this kind of scaling, what happens is the input to a neuron in the next layer basically, or its variance, doesn't grow with network size. It stays order 1. It doesn't go to 0. It doesn't blow up. So everything is reasonable. And so it's a good way to scale things. If you couple this with the right way to scale your learning rates and so on and so forth, something interesting happens. What happens is basically, and this has been proved by other people, and this talk will not concern this limit, so I'll be quick about this. Okay, this network becomes a so-called kernel machine. The way to think about this is the following. You take your inputs X, you pass them through some static nonlinearity. So these guys are not trained. That's what I'm denoting here by 0. Basically, you pass them through this nonlinearity defined by the gradient of this neural network with respect to its parameters. So theta has become W and W plus theta here. And you fix them at initialization. So this is a static map. And on top, you might be training a linear model as the network's output. So basically, what I'm trying to say is training this whole neural network with gradient flow, actually in this particular limit, becomes equivalent to training a linear model after passing input through some static nonlinearity. And if you're familiar with kernel methods, this is a kernel machine. And the particular kernel that's sort of taking action here is called the neural tangent kernel, which is just a dot product kernel of these feature map. Okay, so this was all nice, and kernel methods have been studied for a long time. People know a lot about them. We wrote papers about them. Other people have written papers about them. So we understand a lot about neural networks in this particular regime. Now, of course, I mean, this can be criticized, this particular limit, and one particular sort of criticism is due to its static internal representations. What I mean by this is, I mean, you see these features here. I mean, they are the things that they're supposed to extract interesting things from this data, right? Features from this data. However, the way all this thing is set up, these internal features don't adapt to data, meaning they're set by the network's initialization, and they do not change or differ depending on what data that you feed into this, basically. So this doesn't seem to capture sort of the intuition behind how deep network learning works by extracting useful features from data. And there are also other considerations about performance and so on and so forth. We can go to that if there are any questions. Okay, so the question is, I mean, can we come up with sort of other ways to take this particular limit? Okay, seems to be a useful thing to do, in a way that we're not stuck with these static internal features, but basically get to some kind of feature learning. Okay. And so I'll just introduce my notation here and what's happening in the slides. It's a bit of stuff happening. So for the purposes of this talk, I will be sticking to a general loss. I'll call this curly L. Okay, and then theta will be my parameters. This D will denote my data set. So X's will be the inputs and Y's will be the labels. For this talk, I'll stick to a scalar sort of a label. And I'll have P data points and P for points. This is, physics sort of, convention. And inputs will be D-dimensional. I missed a minus sign here. Forgive me for that. The training will be basically a gradient flow. Basically, we'll just evolve parameters with respect to the negative of the gradient of the loss with respect to the parameters. And then here I rewrote basically this feed-forward neural network in the following way. Basically, in goes X, it gets multiplied by some W matrix. I'm going to tell you what these N's and D's are. I get a pre-activation to the next layer, and this gets propagated all the way to the final layer. There's a final H. I call this, so the picture is a bit misleading. I have just one single output over here. And before taking this pre-activation, let's say, or last layer's pre-activation, whatever we want to call this, through making an output, I'll just scale it again with some factor. And what I've done here is basically introduce, so this eta is a learning rate. This is the parameter that goes over here. This gamma is basically the scaling. So what I've done here is basically introduced, n's and their powers in every place here, which I think you could scale as you're taking, things to infinity. For example, you could scale, the pre-activation basically after, this linear sort of multiplication over here with some power AL, or you could also scale, the initialization variance with respect to some power of width. Okay. Note that these things are not the same because gradient acts on these W's, and so putting this N over here or there that make a difference. You could scale the learning rate with some power of N, and also this sort of parameter over here with some power of N. I put some factors of gamma in eta learning rate because it's going to make my algebra easier, but this is not losing any generality over here. And I'm not dealing with sort of biases here just to make the algebra a bit simpler for these slides. Okay, the question is, how should I choose these A's and B's and D's and C's in a way, as n goes to infinity, in a way that sort of things simplify, meaning there's some kind of simplification, concentration, whatever it is, but yet I get like a meaningful limit where actually there's some kind of feature learning happen. Okay, so in particular, I'm going to demand the following. So at initialization, the pre-activations H's, so this is just the same thing from the previous slide. So these guys are order 1, meaning they don't go to infinity or they don't go to 0. Outputs evolve in order 1 time, meaning under gradient flow, I don't have to wait until infinity for basically things to learn or just too quick. And finally, I'll ask, so this is the thing that's going to make me deviate from basically the NTK limit I just described, these H's themselves also move in some finite time, basically. Okay, so they're not static; they also evolve. So I will call this feature learning. I'm not making a claim about this feature is actually this learning some useful features. I'm just like trying to postulate a limit where things change, internal representations change. Okay, they may or may not be beneficial. That's a different question. We will talk about this. So if you do some, if you just take these into account and basically, study how should I scale things and so on and so forth. I put just a side note. Sorry, I put a root d over here. This is not going to infinity. This is just to cancel that d dimensional vector over there. So this is some convention. Basically, this gives you a bunch of conditions for how you should be taking A's and B's and C's to infinity. And sorry, A's and B's and C's should be sort of scaled. And basically, it turns out the important parameter here is the following for feature learning. So there's this d parameter here, which is basically the n to the power d over here, which scales h mu after passing it through before passing it through the output. You have to put a 1 over root sort of n there. That's what's important. In the next slide, I'll summarize everything again. And the other point I want to make is basically this actually doesn't specify all couplings. There's still 1 degree of freedom left. So basically, you can still choose one parameter and do things, So I'll commit to a particular sort of choice of that degree of freedom. So this was worked out by Greg Yang and in an earlier paper, and we have our version in a paper NeurIPS in 2022. So basically, long story short, turns out if you scale things this particular way, okay, you'll end up getting a limit with limit, in which actually you'll have these internal representations evolve. So I combine that 1 over root n gamma thing with basically the previous layer here. So basically what you're going to do is for every internal layer, you're going to initialize with this 1 over root n scaling. But before getting to the output, you're going to put a 1 over n over there and then take everything to infinity. And this is going to basically end up with a limit where you're going to have features move. Yeah. That will also be root n everywhere. Yeah. That's the only well, I mean, there's also some thing relating to how you choose your learning rate over here. Yeah. 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 Okay. Cool. Okay. Now, so what I'll try to do is basically, I'll try to do two things. I'll try to construct the infinite width limit here. It will give me a mean field theory, which will basically map the learning dynamics of this neural network to a stochastic process. So I'll describe you what that is. But before doing that, I want to just show you some simulations, basically showing that this limit might be actually something we can all study in a lab setting, and we can learn something from it. And in particular, I want to argue that basically, in practical widths, by which I mean well-performing, and like that we can achieve with a reasonable compute, and by reasonable I mean academic scale, so things we can do in our labs and stuff. I mean, we already see these networks behaving as if they are close to their infinite width limit, so it might be useful actually just studying this and in a lab setting do experiments and go back and forth, basically. That's what I want to try to argue. So I'll try to argue this through a bunch of simulations. So the simulations are not exactly done in the particular sort of setting that I'm describing, in the sense that like these are online versus offline. I mean, I allow other kinds of optimization tricks. Basically, the idea of these simulations is try to get these networks to perform well in the particular initialization scheme that I described, and then scale them up and see what happens. All right, so this is, for example, a ResNet 18 trained on a CFAR5M data set. These are hyperparameters. So what you're seeing is basically the test error across basically training steps. And then, and these different lines are basically different widths. So the thing that I'm trying to get at is basically, as you're seeing, in a second, I'll also compare this to NTK scaling. So keep that in mind. Basically, as you get wider and wider, you seem to be already at a limit where you get pretty good match. So you seem to be approaching the limits. So this is a finer level test. So this was the whole test there on the data set. So this is basically the following experiment. we take one of the outputs. So this is basically a 10 clustering, I believe. So you just take one of the outputs and then look at the logit value on a particular test point. So at every step in training, we give the network the same inputs, look at this logit value, and plot that thing across training steps and basically across different widths. Even this very particular prediction, very fine-grained prediction on a particular test point seems to be, pretty consistent. You can even these non-trivial, nonlinear dynamics seems to match across widths. Of course, for this to make sense, we are presenting the same data in the same order to these new networks. Right? So that's the idea. Even other comparisons. So this is histograms. Histograms of what? There's a pre-activation histograms. We go to a particular layer of this neural network, look at all the neurons, and collect pre-activations from them across a bunch of images and make a histogram out of it. This is a log scale on the y-axis, and this is just basically the value of the pre-activation. And the reason we are looking into this is these quantities will be important for our theory later on. Okay. And in the beginning, you expect them to look Gaussians. They'll look Gaussians, and the Gaussians and the widths and shapes are basically consistent across different bits. And this is after training, final. And here you expect to see deviations from being a Gaussian, and you do see these deviations. But even though the particular deviations themselves are consistent across widths after training, so even at this kind of finer level, statistics match. And so this one is another test, last layer similarity matrices. So these are basically, by similarity matrix, I collect representations, vectors, and take dot products of them. So these are data by data matrices. And again, the same, across at initialization, after training, across different widths, you see like almost all the final structure being preserved. And so this was and then again, another sort of test. This is the top eigenvalue of the, I believe, loss Hessian. And you again see some match. So all in all, I want to just make the point that you might already be in an academic setting at a limit where you do see some kind of consistency. So perhaps studying this particular limit for this particular initialization, which already gives you a state-of-the-art sort of performance, at least on these data sets, might be might be a good thing to do. So we can also run experiments in our labs and go back and forth and study them. Just before finishing this, I want to also do the same comparison across these two different kinds of scalings, NTK versus the one I described. I'll call this a mean field scaling. So this blue line over here, so this is again a different kind of a neural network. This is, I believe, a 4-layer, I don't know, a tensor neural network or something. It's not a ResNet, but so the blue line here is basically sort of a baseline sort of neural network, and then we scale the same neural network up using either the mean field scaling or the NTK scaling. So the NTK scaling is the dashed line, and the other one is the solid lines. And as you're seeing again, so we're far away from the limit of NTK scaling. This is going to go up and up if we just scale more and more. But for the particular scaling we're studying, I think we're closer to the limiting behavior. Okay, so to conclude what I've just shown, this is what I'm going to conclude from these simulations. We do observe some consistency across widths for many quantities of interest to deep learning practitioners in this particular scaling. And so we have a recent preprint where we have more experiments you can take a look, which some of which involve things with language models and things like this. And transformers, yeah, right. The question is, okay, now given this, for this initialization scheme, can infinite width limit be descriptive of practical situations? That's what we're going to do. Now, I'm not going to be able to answer this particular sort of question. We're not there yet, but I will actually construct the infinite width limit and show you that it's a complicated object, and then we'll see what we can do from there. So we're there. Okay. So in particular, I'm going to describe you a mean field theory in deep networks in this particular infinite width limit. And the two papers I'm going to talk about are these ones. I want to also compare to, just before going forward, like similar limits were considered by other people, Rotzkopf and colleagues, and Montanari May, and then Greg Yang and colleagues. The difference is, so these two works are 2-layer neural networks. Our application, our construction will be applied to deeper neural networks. And you might be familiar with the MUPI sort of work of Greg Yang and colleagues. So So we will be able to recover the same thing using methods that are, I think, basically familiar to people here, like path integrals and things like this, mean field theory. So we'll end up basically getting similar results. So that's the difference. Okay, cool. All right, so reminder, so this is what we're going to study. So are we going to, everything is going to be the same. This is just a summary slide. I still missed the minus sign over here, and so on and so forth. Okay, cool. All right, so here's the final thing. The training dynamics will be described, so this whole gradient flow will be replaced by a non-Gaussian stochastic process over single-side pre-activations and pre-gradients. What do I mean by this? Okay, so here's the idea. So to introduce you what's going to happen in this theory, okay? So we'll first start by rewriting gradient flow in a different space. So we want to get rid of weights as much as possible, okay? And in particular, we'll try to write gradient flow in so-called feature space. And the key features in this sort of rewriting will be these so-called, I'll call them layer-wise sort of feature and gradient kernels. What do I mean by them? So the first guy over here, so fortunately there's some delay between sort of my cursor here and what's happening on the screen. So, all right. So the first guy over there on the left has indices mu and nu. These are data indices. And L is a layer index. So for every pair of data, we take a dot product of a particular layer's activation sort of vectors. That's what this is. That 1 over n scaling is to make sure that this scales in the right way in order one quantity. And it has 2 time indices. So basically, these T and S are 2 different times across training. Okay, so this will be this is a very key feature. I'll call this a feature kernel, even though it's not really a kernel. Okay, and the other one is a gradient kernel. So in that particular case, these are basically, this is going to be carrying the information that is backpropagated through the neural network's output through gradient descent to a particular sort of layer. And again, that will be constructed by taking 2 dot products of these 2 G vectors, which they are basically formed by taking the last layer's sort of outputs or pre-activation to an intermediate layer's pre-activation vector. So the scalings here are done so that everything is order 1 as n goes to infinity. And to argue that why these are sort of the important quantities, so here's a way to rewrite gradient flow. So if you look at the neural network's output or how it evolves with respect to a particular data point mu, okay, you can show that that basically is given by exactly the statement over here. And what sort of appears in that statement is exactly these sort of feature kernels and gradient kernels, and that's sufficient to write the whole thing. It's just basically some simple algebra over here. The delta here is basically the loss gradient with respect to a particular output. So that's where the loss enters the picture. So as you see, these are the fundamental objects. Sorry? S is an arbitrary time, yeah. So T and S are just 2. Okay, so it's actually good. For this bottom formula, these are all actually equal time. T, everything is T. So these are T, comma T, T, comma T, T, comma T for this particular thing. But bear with me for a second. Okay. All right. So this is actually the full thing. Thanks for that point, Alex. So this is basically the full set of gradient flow equations. So it is written in an integral form. Basically, this is the way this equation comes from is basically you write dh dt is equal to something and you integrate it. And then you see where these feature kernels are appearing here. This is where it's happening. This G is the backpropagation thing. This is a loss gradient. You can sort of start seeing that this is related to the backpropagated error. The Z is related to G. So this is basically carrying the evolution of the error signals and so on and so forth. And then network's prediction is equal time sort of kernels here. Okay, so the reason we wrote this way is because, I mean, so note that the randomness in the system is coming from initialization. We want to separate out the initial conditions so that we can do later on averaging with respect to them. And that's exactly happening here. So the initial conditions are given in this chi and psi sort of fields. If you look at what's happening over them, the chi is basically temporally evolving sort of activations multiplied by the weights at initialization. And everything that's time evolving went into these integrals. So it looks complicated, but it's just like basically integrating a first order differential equation. Okay. And because of this, we will be able to average over these initial conditions and get some sort of mean field description out of this. Okay, so that's the idea. So this is exact. There is nothing sort of approximation here. It's just another way to write gradient flow. It's interesting. Maybe there might even be some new things that's coming out just by looking into this. If you were running various data, so phi 0 is just x transpose x. This is the data kernel. That's where the data is. And the other way data enters here is chi L, chi 1. It basically depends on input. That's where data enters. Okay, cool. So what am I going to do with this? Okay. So here's what I hope to see in the n goes to infinity limit. I mean, I hope to see this after I did the calculation, but I know it's going to come out. But just to give you what's going to come out. So basically, these kernels, because I'm averaging a bunch of quantities as n goes to infinity, sort of, I hope that they're going to concentrate, meaning they won't have variance with respect to different initialized neural networks. However, they will evolve in time. This will be the difference from the NTK regime, where they are static in time, but they will evolve in time, but they won't have variance with respect to different initializations. Okay. So the other thing that's going to happen is basically sort of there will be some kind of factorization of the joint distributions of activations and pre-activations across a layer. Okay, so they will be IID distributed sort of across a different layer. I'll be more precise about this. And then what that means is I will be able to replace these sort of dot products over here, okay, and with respect to averages, with respect to these sort of single site activations. Okay, so, and the way we see this happens is through just one slide about like this to this audience, through sort of a path integral like formalism. This is in statistical physics, this is the Martin-Sugiero formalism. So what you do is basically you introduce a generating functional for some of these fields, and you try to average them across initializations. Okay, so this is basically giving you time-dependent correlators of sort of all these fields. And then what you do is you insert in here a bunch of delta functions that basically impose the dynamics on these chi's and xi's. So through these kinds of sort of field delta functions, and then just do these averages. And the averages we can do them because we have separated the initial conditions from the dynamics, so we can just do these averages. And at the end of the day, okay, as a standard sort of after standard series of manipulations, you end up with basically the partition function written in a form where you have these, you're integrating over these sort of order parameters, if you want to call them, or these kernels that I just described to you, plus two fields I didn't tell you about yet, but I mean, I'll not, but there's some extra things about one, times some exponent of some action and described by, and in front appears a large parameter width. And just looking at this action, you can derive, sort of see what's happening. And that action describes exactly this sort of crazy looking stochastic process. I'm going to tell you what's happening over here. Just want to point to you that this ends up basically matching the result from tensors programs from Greg Yang and colleagues. So, but you're able to get them from all this sort of standard path integral kind of formalism. And am I running over time? How much? 3 minutes. Oh, excellent. Okay. Right. So, great. I think terribly over time. Okay, so I'll be quick. So what happens in this particular limit is, so notice that these H's now lost their sort of I index, which was counting the number of which neuron they are in a particular layer. Instead, basically, what this describes is the temporal evolution of the distribution of activations and pre-activations across each layer. Okay, so basically that's what's happening. Okay, so I'm not going to the details of this. To be able to solve these equations, you need to go through complicated sort of procedures. I'll skip this also. Okay, Monte Carlo procedure, but I'll just show you some simulations. So this is a simulation of a sort of depth 4 with whatever 4,000 something neural network. And here you're showing in dashed lines is our predictions, the DMFT predictions, by which we get through solving this non-Gaussian stochastic process. And the solid lines are basically the network training. There are other lines here. These lines correspond to different learning rules. So we were able to do this not just for gradient flow, but other things like feedback alignment and so on and so forth. the same procedure works. This describes, for example, the particular statistic we're describing, the distribution of activations before and during training. And again, the dashed lines are DMFT predictions, and sort of the solid lines are simulations. So DMFT can capture all of this. And these are the kernels that are described by theory and experiments. I'm running terribly over time. Okay, so this is describing basically comparing the DMFT in this particular limit to other approximation schemes, which involve things like NTK limits, some perturbation theory, which is a small gamma perturbation theory, and then other things. I mean, the DMFT works, but it was designed to work in this limit, so it's not really too informative. I'll skip this. Okay, so, but the point is, I mean, this is a complicated stochastic process. What you can do with it is limited in a sense, so far has been limited. So we can simulate them for small neural networks and so on and so forth. But we can connect the previous results. For example, for two-layer neural networks, you can derive a PDE version of this dynamics, not an integral equation version of it, a differential version of it. So which ties to the previous sort of two-layer neural network sort of DMFT limits, mean field theory limits, which were also sort of PDE descriptions. And for linear networks, actually, you can show that everything turns into a stochastic Gaussian process. So you can express everything in terms of means and correlators and so on and so forth. And instead, you can come up with just a set of deterministic algebraic equations. And you don't have to have a complicated Monte Carlo procedure. And solving them in certain versions, you can recover known results. Okay, so I'll skip this one. But all right, so I just described you one particular extension version of this. If you go to the appendices of this paper, you will find extensions to discrete time, Langevin dynamics, meaning I add a bit of a Gaussian noise to sort of gradient flow, rate decay, multiple outputs, CNNs, and all these sort of limits can be constructed. So to conclude, so we do see in this particular scaling consistent behavior of networks at academic scales, I'll call them. And I showed you a construction of a mean field theory in this particular with infinite limits. The question that still stands is this the right theory? Does this mean field theory actually describe what's happening in these resonets and so on and so forth? That requires us to come up with clever ways to simulate. So we're working on that. I hope to report on that when we get the answer. So with that, I just want to finish sort of by thanking sort of the people who did this work. In particular, Blake has been spearheading a lot of the theory here, and other folks also were influential and helpful in getting all these simulations. And actually, the first part of the talk was spearheaded by Nikhil. So special thanks to them. Thank you, and sorry for going over time. Thanks.
All right. Thank you for the talk. All right. Yeah, 15 minutes for questions.
Oh, 15 minutes. Okay.
So I had a question about, you're very careful to say always academic scale training. Do you suspect that larger scale, like whatever, large language models, industrial scale stuff is different qualitatively or quantitatively?
I mean, so I think it's an open question, so I don't have access to their training dynamics to test them. So, but maybe since we have a lot of time, I can use this to give you some slides about convergence and so on and so forth. So this basically is showing the convergence of these networks, simulations to the infinite with prediction. Okay, so I'm comparing measured quantities at finite width. This is n, and to the infinite width quantities that we compute through these Monte Carlo simulations. And you see basically some 1 over n. These are squared quantities. So it's exactly what you. So you do see some kind of 1 over n sort of convergence. So this is good. We have to be careful about like the particular sort of limit that these equations were derived. So I'll have to go back and forth a little. I'm sorry. All right. So there was a note here which I did not read, but I should point. Just looking into these equations and the way we derive them, the kinds of sort of manipulations we do is valid in the particular limit that the sample size is basically order 1. It doesn't go with width. So this actually also assumption was made in the previous mean field theory works that's working in this limit too. So that might be some kind of a sort of a problem. So you'd be careful about, because if this is, my understanding is in modern sort of larger scale networks, this is not true. I have a reason to, okay, but then, so going back and forth, I'll show you some more sort of simulations. So we have a recent preprint I haven't talked to about. So this is basically doing the following thing. So we drive this stochastic process through this saddle point, right? So you can basically try to go to next order in 1 over n and so on and so forth. And from there, try to see basically some predictions about like when this is, when the leading order is going to break down and so on and so forth. It turns out to be a hard thing, so I'm not going to go through the equation, but I'll just show you some simulations. Okay. So here, what I'm showing, so this basically shows that this is a 2-layer linear network. This is the simplest case we can work analytically. Left-hand side is showing that basically our calculations can capture the variance with respect to the predictor, which was supposed to be 1 over n. So this is n times predictor. That's what it's showing. But this is sort of more interesting over here. So the dashed lines are the infinite width DMFT limit. Okay, and sorry, the black dashed line is the infinite width DMFT limit. And the other ones are basically 1 over n and corrections included into this sort of infinite width limit. Okay. And the point I'm trying to make is as you keep adding more and more data points, basically even the 1 over n corrections are not able to save you. And so we have some reason to believe that basically the right thing here might be p over n, but this is work in progress. So so whether this applies to industrial scale or not, I think is an open question. I don't think this really kills it because I think the consistency experiments that we're running, okay, actually show that, I mean, still there might be a way that this whole expansion saves itself through some other mechanism, but that's an open question. Yeah, I'll go with that. Yeah, sorry. We'll get there, sorry. Yeah, go ahead.
Thanks, Cengiz, for the talk. So both in your talk and when I hear Greg Yang talk about UP, it's about taking a small system and trying to say, how can I replicate that behavior as I scale up?
Yeah.
Of course, the other way you can think about it is saying, here's my desired behavior that I can derive from the infinite and limit, and how do I actually go down to academic scales to get a type of desired behavior?
It's an interesting question, yeah.
And so my question is, you made a choice at some point. You said, look, if I want to have this feature learning behavior, I need to have this d equals a half, but you had this freedom. I guess it looked like there was, is it 1 degree of freedom or 2
There's
degrees?
1 degree of freedom left, yeah.
So, and you made some specific choice for that 1 degree of freedom. If you adjust that 1 degree of freedom, is there anything interesting to say about this relationship between the limit and what you would do at academic scales?
It's good. If you haven't tested this, but looking at the equations, I believe they all lead into the same dynamics, actually. So that 1 degree of freedom should give the same dynamics, but this is something we need to test. Yeah, but just looking at the equations, it looks like so.
But I would say that there's basically only, at least within this context, there's only one type of feature learning possible.
Yeah, yes, this particular way. Given the assumption that I've made, of course, you could have chosen, for example, I don't know, H is to not move in order 1 time, but some power or something and something, yeah. There was a question over, Alex. Yes. You had the same question. Okay, excellent.
Sorry, one more question. So you had one plot near the end where you're comparing the theory to the, I guess, to a simulation, and they are exactly aligned. But that's a smooth curve. But you had a plot before that seemed somehow more realistic because it was, a little bit more spiky. The test loss as a function of time. Like these curves are very smooth.
Yeah.
So what's the difference between this plot and the one from, I think it was, you were comparing how different widths are all consistent with each other.
Sure. So it's a good one. So this is, this is a simulation. We're looking at test loss. I mean, even here, you start seeing some kind of non-smooth things. For example, if you look at this final, so that this is a histogram of H's, right? So if you look at that final one, you see these peaks and nonlinear peaks. And so, I mean, the DMFT captures this. By the way, the reason this is happening is because, there are some deluges here and actual tensions actually. Basically, things beyond 0, if you go too deep, actually don't contribute much. But, sorry. You were comparing it to this particular thing, for example. Right? So If you look at an aggregate measure like test error, you do see again like smoothish behavior. I mean, you do have some stuff over here probably. This particular zigzag one is a very particular sort of metric. So this is actually not like a global, I don't know, error measure or something. It's exactly the logit value, even before passing through, softmax and stuff, of a particular output given a input. So you do expect it to like vary pretty wildly, and then that's what's happening. The interesting thing here is basically, again, like even these variations are captured by Christopher bits.
Hey there. I really like this.
Good to see you, Jay.
I wonder if you could say something about the computational cost of simulating the system.
Yeah,
I know
so
that
this,
like
yeah, this is
that YAG's perspective, it's like exponential in time, and I think number of data points, but it seems like you have like a set of consistency equations that you might be able to iterate somehow, or
yeah. I do have slide on this somewhere in these slides. Sorry. Yeah. Well. Yeah. So so basically, we can look at the last layer over here. I mean, so P here is basically number of data points, N is width, and time is the number of training steps. Basically, you can read it. So full DMFT is basically what we are running this thing, and with N, a neural network is basically here. So basically, if you want to use this as a sort of way to simulate neural networks faster, I mean, this only works if the width is much larger than P times T. P being the number of data points and T being the number of training steps. So then this will be actually a faster way to sort of simulate this.
but everything is polynomial. There's no like exponential in.
Why would you expect that? Maybe exponential in what? Like width, you mean?
My understanding is that if you take like the mu-p parameterization, for instance, and try to work out like the training dynamics in discrete time for many steps, you end up with equations that are exponential in the number of steps that you are simulating.
Okay, I mean, it might be that so I mean, maybe we could talk about this offline, but this refers to the particular stochastic process and the way we did solve this. It might be maybe there's a simplification here that's not in that particular sort of equation. So yeah, but happy to talk about that. Bye.
I think we have time for one last question.
I think at the beginning, one of your assumptions was the weights are initialized with a normal distribution.
Yeah.
How does this change if you use, say, the PyTorch default of a uniform distribution?
I mean, a good one. At the level of theory that we're working with, as long as a central limit theorem applies, it should be fine. So if you have a bounded distribution, the second moment is basically there, so it should be fine. Yeah, I mean in this business, there's also certain formal proofs that people have, for example, tried to prove NTK limit and so on and so forth. And there, people have assumed Gaussians, but in the physics, let's say level of rigor, as long as you have a central limit theorem, it should be fine.
All right. Thank you for all the questions. Let's thank our speaker once again.